So when I've been discussing ergodic theory, we've thought about a number of things. I put some crucial problems up at the beginning, and one of which is, do the ergodic means converge? Another of which is, let's attach some invariance to systems and see whether they can be equivalent or not with those invariants. And those have been two themes right throughout the whole series of lectures. We talked about entropy as an invariant for amenable group actions, and yesterday we talked about some invariants for non-amenable group actions. For non-measure preserving actions, and I think that there are which are kind of related to entropy in some ways. But so far, I've pretty much exclusively discussed amenable group actions, and I thought that to complete my survey of the area of ergodic theory related to harmonic analysis, I should try to say stuff about the non-amenable group actions, because there's been quite a lot of interesting work done in that case. So there are two important classes of non-amenable groups. One's the free group on ND generators, and the other are semi-simple Lie groups. So I'd like to spend, I'm not sure how much time there will be to say things about semi-simple Lie groups, but today's lecture is devoted to trying to tell you what happens in those two cases. So first of all, I'd like to describe to you what happens. I also have to say something about the free group. I'd like to describe to you what happens with ergodic theorems. See if I can get these. So what is the free group? So this is chapter 5 in my notes, non-amenable group actions. So the free group, which is written FD on D generators, take A, the set of generators, with the cardinality of A being D, and we'll let S be A intersection A minus 1, so that so the free group is the set of all words in S with X never adjacent to X minus 1. And if we put two of these words next to each other and find an X and an X minus 1, we just cross them out. So that's the delta function on the word W. You can imagine adding up over all possible words some constant times the word. That's the direct Dirac measure. And in particular, there are some means on this. In fact, which are going to play the part of our ergodic averages. So Sn is going to be equal to the set of all words x such that the length of x is equal to n. So the length of x, of course, is the number of symbols in the word x when you've reduced it down and removed all x minus 1s from it. Maybe W is a better symbol to use here. W. So that's some kind of sphere, if you like. We'll think of these as spheres, and we're going to formulate our ergodic theorems in terms of adding up over these SNs. I will also probably use nu n, which is the Cesaro means of these things. So how, in this context, do I start formulating what might be an ergodic theory? We want to have projections onto invariant measures and those kinds of things. It turns out that there's a very exact analog, started with Givash, and then Amos Nevo and people like that during the mid-90s have actually proved very exact analogs of the ergodic theorems in this setting. And so the first topic is to describe those to you. So if you can find a representation, and I'm thinking really largely of using it in L2 of Fd, then we can of course take what we might call the Fourier transform of one of these mu's, or in fact of sigma n, and write it like this. That's a bounded operator, and let E1 equal the orthogonal projection onto So pi sigma 1 of the words of length 1, well, they're just the individual generators, and the invariant things are going to be the things in the image of pi sigma 1 minus 1. That means it's invariant. And E minus 1 so our ergodic theorems were formed around the context of if I take a limit of sums of this kind, are they going to approach these orthogonal projections? That's how we formulated all the ones for amenable groups, and that's how one can formulate So I guess one of the earliest theorems proved by this was due to Guy-Varche. If X is a compact metric space, with an action of by isometries, and FD2 words of length 2 acts transitively then there's a unique probability invariant probability and the limit as n goes to infinity of pi sigma n f equals the integral f d. Did I give that? Yeah. For every f, for every continuous function x. So this is not massively difficult to prove. The fact there's an invariant probability follows from the Krylov-Bogolyubov theorem that I mentioned the other day, and then you use our Taylor-Ascoli theorem to show that there's a uniform convergence here. There was still the question about, well, now let's assume that now let's suppose that FD acts on a measure space, not a compact metric space. So then so Nevo then proved, sort of generalized the Guy-Varche theorem to measure spaces in terms of the kinds of language we've been using and these projections E1. So here's Nevo's theorem. Supposing f is in L2 of x mu, converges almost everywhere to the expectation of f given I2. It's not quite as good as you might want because you have the invariant vectors under the square words of length 2 only, but anyway. Did I write F? Yeah, I did write FD2 there. So, in fact, if you take this as arrow means, then you actually get convergence to an invariant function. So that converges onto the E1. So it's really really this is a reasonably exact analog of what we had in the previous cases. And the proofs are not terribly different. You have to establish there's a telescoping sum argument, just like there is. You have to prove that it goes onto the orthogonal projection of this operator here, and it's very much in the same spirit as the very first theorem we proved at the beginning of the lecture. Once you've set up the algebra is right. And in fact, so he showed the LP convergence and almost everywhere convergence with these Cesaro means. So I do want to say a little bit about the proof which to prove the L2 convergence, you really need to have we needed some analog of the Fourier transform, really, and it isn't quite there, but if you look at the commutative, it's really a C-star algebra proof, I guess. Maybe I'll write C rad of f d So a radial function is one which has the same value on all words of length n, and therefore the words of length n, sigma n is the unidistributed lattice on the words of length n, and if you take linear combinations of those, then that gives you a set of radial functions. And well, it's not quite. The thing that makes it tick is, in fact, Guy-Varch's lemma, which he proved in the course of proving this theorem here, is that tells you what happens if you convolve sigma 1 and sigma n. There's a lovely little computation you can do looking at words and taking a convolution like that, and you see that if I convolve sigma 1 and sigma n, I get 1 over q plus 1, sigma n minus 1, q over q plus 1, sigma n plus 1. That tells you what the commutativity of the sigma i's look like, and then you can work out the spectrum of that algebra in a very clear way, and that's sufficient to be able to prove the pointwise ergodic theorem. There are some more details in my notes, and it's reasonably easy to find this stuff written down, and I'm just going to say no more about the free group on degenerators in terms of summability. So similar techniques give summability for the semi-simple groups. So it turns out that, well, we need some analog of these sigma n's for semi-simple groups of rank 1, and ideally we need to find some commutative algebra, and, well, you can do that. Actually, that's fairly simple to work out what it all should be, and then there's some technicalities involving the proof, of course, which people like Becker and de la Harpe and so forth have actually worked out. So I'd like at least like to tell you what the sigma n is. So there is a relationship, of course, between you can kind of think of the discrete groups as a kind of the free groups as a kind of discrete analog of the semi-simple groups, as we've all seen somewhere, and So it's maybe not so surprising. And so we all know that L1 k-invariant functions are a commutative algebra because GK is a Gelfand pair, and therefore you get a commutative algebra along the lines of, so you can really study what the Harris-Chandra has given character formulas for that. You can study the spectrum of that commutative algebra. So that's the path we follow. And the spherical means so you take an element of the A part of the Iwasawa decomposition that's indexed by a T, and then that gives you an average over K. If you average that over K, then you get the spherical means. And therefore you have some analog of the sigma T's to formulate what an ergodic theorem might look like. And there are nice Harris-Chandra formulas for the characters. You can look how to convolve them, their limiting things, and so we can establish. So there was some work of Eli Stein on maximal functions on semi-simple Lie groups that was used, and well, you come up with the following. That's the projection onto the